All right, so what we're going to do is, first of all, find dy dx in this case, and then find our slope, find the equation of the tangent line. So if we think about differentiating, let's do left side first. I would have 3x squared if I differentiate the x cubed term. Then on the other side, I'm going to have 3y squared. But since there's a y, I'm going to follow by dy dx. Then on the other side, I've got to use product rule on the xy part. And I think it's easiest in this case if we do first function, second function. So our first function, 9x, and then the derivative of the second function with respect to y would be 1. So multiply by 1, and then dy dx. So you can put another multiplication dot, 9x times 1 times dy dx, or you can leave out that 1. But that's only the first part for our product rule. The first times the derivative of the second plus the second times the derivative of the first. The derivative of the first is just going to be 9. So since we're looking at the derivative of 9x, there's no y involved there, no dy dx. So any questions on that first step with matching up with what you tried? Okay, so let's take a look at how to clean this up. Notice this one is a little bit different in that we have a dy dx on both sides, but we're just going to arrange it so we have our dy dx's together and everything else on the other side. In other words, get dy dx equals. Now, if I'm doing this, I'm just going to clean up my line here because I really don't want to see that times 1, and I would really like to write the y times 9 as 9y. Okay, so there's my equals. You don't have to continue to write the multiplication dot in between the 9x and the dy dx, but it's helpful just so you don't forget that multiplication. So then what we're going to do is move this piece to the other side, 3x squared, get it moved over, and then we'll have 3y squared. Notice the terms with our dy. So 3y squared dy dx minus our 9x times dy dx piece, moving this piece over, this guy over. And then on the other side of my equals, I'm going to keep the 9y that was already on the right side, and then I'm going to be subtracting my 3x terms. Okay, so some rearranging, and then we're going to use a technique of factoring out our dy dx. So here's your dy dx. Factor it out. And we could use a parentheses or a bracket, doesn't matter. This gets kind of messy because notice we still haven't found dy dx equals. I'm going to try to squeeze it in right up here, guys, so we can keep it on the same page. So our dy dx equals 9y minus 3x squared. Can you guys, I'm not sure if you can see that behind the picture. On mine, the picture is blocking it there. And 3y squared minus 9x is going to be our denominator. Now, complicated looking derivative, we've got some symmetry happening, but at this point, that's the expression for the derivative at any x and y value. It's not focusing on a specific x and y value. So let me jot that down so I can make sure I get it correct on the other page. We're just going to take a look back at our problem. So our problem is to find the equation of the tangent line at a specific point. So now is our time to plug in the x and y that they gave us into our expression for dy dx. So I'm going to go ahead and write our dy dx again. And what we're going to do is plug in x equals 2, y equals 4. And sometimes when we do this, we put the 2, 4 right here, just this bar, to denote we're plugging it in. So let's do that. And I'm going to just switch over to slope, right, because the derivative at a point is the instantaneous slope. Instead of this kind of clunkier notation, this is giving the instantaneous slope to our implicit curve at a particular point. Now, most of the time I pop these into Desmos to evaluate. This one's not too bad. All right, so we can do this. We've got 36 on this part, and then 2 squared gives us 4. 6 minus 12. And then we look at this guy, we've got 4 squared gives me 16. 16 times 3 gives me 48. And then minus 18. Okay, so let's put it together. So let's see, if I do 36 minus 12, that gives me 24. I'm not making any careless errors here. And then below, when I go ahead and divide, or sorry, subtract, I get 30. Okay, so 24 to 30. Again, we don't care too much about simplifying most of the time, but it's going to help us look a little bit better. In this case, notice 6 goes into both. So 6 goes into 30 5 times. 6 goes into 24 4 times. So we can reduce to 4/5. And this is the slope that we're looking for. Now, remember, if you have a slope, the next page, of 4/5, and the point is 2, 4, a slope and a point is enough to give you the equation of a line. And I'm going to, just because it's easier for the Desmos activity that we're going to do next, instead of using y equals mx plus b form, I'm going to use y minus y1 equals m times x minus x1, point slope form. Okay, just because it's easier in this context. It's a little bit cleaner. So what we're going to do is just plug in. My y1 is 4, slope is 4/5. My x1 is 2. Now, could you go ahead and clean this up and solve for y equals? Sure, but you don't have to. If you have the directions to find the equation of a line, unless they tell you to put it in y equals mx plus b form, this is okay. So just watch out on MyMathLab. I don't remember how many times they specifically ask you to write a particular form in this section. I'll double check that, let you guys know when I send the video out. But what we want to do now is pop over to Desmos and work on checking this stuff, right? Because we've solved the problem, but we want to make sure it works. When you have an equation and a tangent line, Desmos can help you visualize to make sure your tangent line looks right. Then we'll see that we can expand on that idea to get in a sense of checking for others. I'm going to stop the share. And then I'm going to pop us over to Desmos and share that screen. And in this particular case, notice that I went ahead and graphed my function already. So this was the original function we started with, x cubed plus y cubed equals 9xy. And notice this is kind of our loop. Now I want you to go ahead and think about where 2, 4 is, since that was our point of interest. 2, 4 is on our curve. Now, if you think about a vertical line, 2, 4 is not the only point with an x value of 2. Notice we have another point down here. That's why it's important to have two coordinates, the x and the y, because the x and the y coordinate give us a spot, whereas if I just said x equals 2, it could have been either one. Now, in some cases, you could have the same slope, but in this case, it doesn't look like they quite have the same slope. The slope down at this portion looks to be less steep, this one a little bit steeper. So here's what we're going to do. We are just going to take our tangent line and see if when we plot it, it looks like a tangent line to our loop at this specific point. So y minus 4 equals 4/5. times x minus 2. Beautiful, right? So in this case, this looks great. Questions here? Even though it's more work to find the equation of the tangent line, I think these ones are easier to check or more straightforward to check than what I'm getting ready to show you. So what I'm going to do is go ahead and take a look at the way to check the rest of these. And we're going to refer back to some of the ones that we have already done. And what I want you guys to do is go ahead and go to Desmos, student.desmos.com. Go ahead and put in this code. Give you a minute or so to do that. And we're going to go through the activity together, and I'm going to show you how it allows you to check. And what I'm going to do, let's see. Colin, I see you're in. I'm not sure if I can type that into the chat. Colin, can you try, since you are already in, can you type this code into the chat? For some reason, it's not letting me pop the chat up. Oh, here we go. I don't know why it's letting me chat to each of you. Oh, perfect. That way, if anyone else pops in, they'll see the code that we're looking at. Oh, there you are, Grant. Okay, that way we've kind of got that as part of it. All right, so clear this stuff out of the way. Making my group chat go away there. All right, so these first few slides, we don't necessarily have a type and answer right now, but nothing more than a couple words. What do you guys think on this one? You can either put it into your Desmos or you can type it in the chat box, either one. I didn't create this particular one. I added a few to this that we'll see. So I'll share with you what I think it kind of looks like, or what a lot of students said last semester. They said it looks like a wagon. So if you think about like this part as the mountain, and then this part maybe as the wagon part, you can kind of use your imagination, stretch your imagination in this case, to think about a little Oregon Trail wagon bouncing down the road. So let's take a look at our next one. So again, kind of same thing. What does it remind you of? A lot of people said like a fish, like a really rudimentary fish sketch, or a loop-de-loop. But the idea on both of these is these are implicit functions, and they're implicit functions that we can actually differentiate and find the tangent line at any particular point, the slope of the tangent line at any particular point. So this next slide on number 3, the hard part is if you're not looking at one specific point and one specific tangent line, like we just did in the last example, the coding on Desmos gets a little tricky. So I put the coding in here to walk you through it, and this is how it goes. Our goal, so on the following pages, I will provide you with some unique implicit equations. So I'm going to give you the implicit function or the implicit equation, and your goal is to find the implicit derivative, dy dx, via paper and pencil. Do that first. Then we're going to plug the formula that we find into Desmos and see if it checks. So what we're going to do is the dy dx that we find is going to be a function, and we're going to call this function m of xy. It takes 2 inputs and gives us 1 number as an output. It uses the x and y to plug into that formula and get the 1 number slope. Then we're going to have a point that we can move around already on the screen, and our m at AB is the slope of that point. We're going to take that slope and the point, and we're going to put it into point slope form. So notice in this case, if the point is AB, notice point slope form, we've got y minus y1, y minus b, and then this part, x minus x1, or x minus a. And then we're using this m of ab, which is a function pulling the a and b value and determining the slope as the slope point. So it's a little bit more complicated in terms of coding, but you'll see it's not that hard to get the hang of. Then we're going to move the point around and watch the tangent line change so we can track our tangent line. So we're going to start with kind of the easiest one. We did this one already, and let's take a look back at our notes. This was actually our very first one. We found in this case that we didn't have to use product rule, made it a lot quicker. And what we found was, once we cleaned it up, dy dx is negative x over y. So I went ahead and started the coding on this. Type in below your formula for your implicit derivative as m of xy. That's where we're going to type negative x over y. And right now, this doesn't quite look what we think it might. This red point right here is movable, but it's not stuck on the function, if that makes sense. In order to check this, you have to move the red dot, first of all, to your function, and then you're going to be making sure it looks like a tangent line. Now, it looks like it at this point. Maybe we can just kind of see it's touching in one place. But what our goal is to slide it around our circle and make sure our line continues to look like a tangent line as I do my best. It's not going to be perfect to keep this red dot on the exterior of the circle. So notice as I move this dot, notice that equation of the tangent line. It's not, whoop, I got a little off course there. It's not displaying those values out here, but the coding is continuing to change our slope. Now, let's say that you did not get this right. And let's say in your original dy dx, you just left off the negative. So this is what it looks like if it doesn't check. As you move this point around the circle, that blue line is not a tangent line. Pretty simple check. Now, this part, the x over y, is all you had to fill in on this slide and actually the next slide. On some of the other slides, you've got to just retype this part, the y minus b equals m times x minus a, or m of ab times x minus a. So I'm just going to put that negative back. Looks better. And let's try our next one. So our next one, this is actually the one we just finished up. This x cubed plus y cubed equals 9xy. We were looking specifically at the equation of the tangent line for 2, 4. But if we take the dy dx that we found and plug it in here, we should be able to slide it around the curve and kind of move it to 2, 4, but then other places. So if I look at this one, if we look back at your dy dx, is 9y minus 3x squared over, that's not what I wanted. Put that 3 on the bottom. 3y squared minus 9x. Okay, now this doesn't look too bad right now. Notice my point's not really on that curve. So if I drag my point to the curve, but try to drag it to 2, 4, that looks good. But as we move it around, got a little off course, looks good, okay? So I'll pause here. Questions on this one? So in this case, let me just show you what you're going to do on the other side, so we won't go through the other ones together. But this also gives you a really cool way to check any problem you have in your homework. If you're getting it wrong and you're not, or if you're not sure if you're getting it right and you want to check it before you kind of do the next step, delete this part, put in your function. Delete this part, put in your dy dx, and it will graph your function, and then it'll graph the slope line that you're telling it to. So I can go over that a little bit more if we need to, but it gives you a way to just substitute the function, change your derivative, and use this. And it's okay, just as a quick note, to I'll make a copy of that coding to put on your next test so that you can kind of use this to check as well. That would be acceptable. So let's take a look at the next one. So this is slide 6. On slide 6, this is the bouncing wagon one. And on this one, there's one change in the coding that you'll want to make sure you notice. Notice our function is different. But if I just look at this function quickly, there's no products. So even though I have a bunch of stuff, I have a bunch of y's and x's, I do not have an x times y, or an x squared y squared, or x cubed y. No product or no cross terms. Now, notice right here, it says type in below your formula for your implicit derivative. Here's how you have to start it off. In other words, I just didn't paste this part in before I copied it over. M of x y equals, and then you put it in. Okay, so whatever your derivative it is, you work it out, paper and pencil, doing the whole implicit differentiation method, stick it in there. Then the next part, here's what I would do, because I feel lazy sometimes, is I need to actually write that equation with that point slope. It's the exact same thing that you saw over here. In fact, you don't have to like put the specific function in. You just kind of do a copy and paste. That's the quickest way, or type that part in. Copy and paste works. And that's going to allow you to graph the tangent line symbolically with whatever you're putting in on line 3. So I want you to finish and try this on your own. I don't want to go through every single one right now, but let's take a look at what's ahead. Number 7, it's going to ask you about horizontal tangent lines. Remember, this is a flat line. Now, on this curve, notice it looks like there's potentially more than one place. In fact, it turns out that there's 9. Some of these you have to zoom in for, because you could have flat spots kind of at the bottom of this, like if we really exaggerated this dip kind of at the top of the mountain, maybe we could kind of make it more clear. But then we have some flat places here, like at the bottom of the wheels, possibly. Don't get too stressed out over finding those 9 spots. As long as you can find more than one, I'm pretty happy. Now, there's 2 more that you're going to look at. On slide number 9, you had a new function. This one we have not done together either. It's not one of the examples that I had. And for this one, you're going to have to do the coding in here. So you'll have to type m of x, y equals, and then paste in your expression for your tangent line. This one involves a product. So what you want to watch out for is this xy squared term, and look back at the ones where we use the product rule to get that right. Then you're also going to have, this is like a challenge. If you do not get this one, don't worry about it, right? I'm not going to grade like completion of 10. It is pretty tough. However, if I decide to stick a bonus on the test, finding this one, like the dy dx in this case, or m of xy, would be like bonus level essentially. And then you can check it if you manage to get it. So what this means is, since we did those first few parts together, when you guys go in and finish this, you will just need to finish the bouncing wagon and then number 9. So that's going to be 2 for you to do that both involve product rule. So any questions on what you need to be doing to finish up this Desmos activity? Okay, so what I'll do, we still have plenty of time, is Grant, I think you had a couple questions on the other Desmos activities. We'll just pull them up and look at them. And Colin, if you want to kind of track along with that and look at the questions and see if you have the same ones. And if not, if you want to stay on and work on the implicit differentiation, see if you have any questions while we're still on, great. If you have something else you need to do and you want to pop off, that is fine too. I'm going to leave the recording going through this because there's probably other people with the same question on those optimization tasks. All right, so Grant, if you will unmute yourself and let me know, was it part 1 or part 2 that we had questions about?
Optimizing task part 2, I believe.
Okay, so I'm going to go in and open that one up. And what I might do, just for the people who are watching this recording later, is kind of pull up other people's answers if we need to look at those. So, sorry, sometimes I make multiple copies. You can see lots of Desmos happening here. Let's make sure this is you guys. Yes. I actually have a distance 263 that was online from the start, which is why we see duplicates of those activities. So, yay, lots of people have been doing work. Wonderful. So, Grant, what slide do we want to go to?
Slide 12. is where I kind of want to start at.
Okay, sure. Okay.
So basically what I did is I just kind of looked back at slide 9 and just kind of plug those numbers into slide 12, which I
Okay.
think that's what I was asking for.
And let's just look back at slide 9. Okay. Yes, it is. So what it was asking you to do is think about the boxes that you create here, which hopefully these are boxes that met the specifications. So if you're watching this later for the rest of our class and your graph doesn't look like this one, maybe we need to make sure we didn't mess up kind of how those points work. In other words, kind of misinterpret our original part. So let's assume that this is correct, like this box is correct.
Mhm.
Notice on this one, your cut is 0 and your volume is 80. When we go to
12 times 0, yeah.
this part, I think what it tells you to do, let's see,
0, yeah.
X represents the length of the square cut and Y represents the volume. So pay attention to just that first column and the last column. So we're going to have a 0, 80, 148, 248, 324, as long as all the numbers in your table are correct.
Okay, so 3 inches is supposed to be 80 volume?
So let's see, if 3 should be, well, if X is 3, your cut is 3. And then your other two that you calculated, if you multiply those together, gave you 24. So according to this, you should put 324 into your table, 248, 148, and 080. Let's do that. And then if we're not happy with the shape of that graph, if it looks like what in the world is going on, we can always look back and make sure we did the length, width, and the height right for those particular X values, those cut values.
Okay, and one question about this slide 9.
Sure.
Well, volume is length times width times height, right?
Yes.
Okay, so my volume for 0 cut would be 0, would it not, instead of 80?
Exactly.
Okay.
So yes, so sorry, I think we said that briefly. And then yes, that one is actually going to be 80, which allows you to hit the origin, which is kind of a good thing. In other words, if you don't make a cut of 0 inches, you're still left with like a flat piece of paper or a flat piece of cardboard. There's no point. And so it makes sense that no box should have no volume since we're still 2D. Okay. So on yours, let's see. Let's go ahead. I'm going to take us back to slide 9 just so everyone in here can see. I think if you're changing it, I'm not sure if it'll automatically change on here in lifetime. So I'm just going to write down that table: 0, 80, 148, 248, 324. And again, that's assuming that that table is good. For those of you watching, if you didn't get those same table values and you're watching this later, we can always take a look. Okay, so notice I think all this table, we just kind of need to modify.
Yeah.
Because what we're trying to do is some sort of maximization problem, and we want to make sure we know what we're maximizing and know what we should be looking at on this graph. Let's make sure I got that table in right. And oh, let's see. Sorry, I wrote that needed to be 0 and then I didn't put it in there. So 0, 0, 148, 248, 324. Now, this actually looks fairly decent. If you think back to the frame, the part 1, the frame when we plotted those points actually formed what looked like a parabola. We went up as our cut got bigger, we increased the area, we were in 2 dimensions, but then there was a maximum, and as we made the cut too big, Then we started to get a really long skinny frame and our area decreased again. So this one, you kind of have a similar shape. It's going to turn out not to be a parabola, but we're going to think about the volume at some point is going to be maximized. And that's going to be our y, the volume, the max volume. And then if we think about the x, that's going to tell us how big to make the cuts. Does that part make sense?
Yeah, you're good.
Okay, so let's take a look at kind of this next one. How did you feel about making those equations, like the equation part?
I was kind of looking back from, I think,
Oh, and I got the slides wrong. I chopped.
yeah, that's why it kind of mixed me up a little bit.
Yes, I apologize about that. I chopped it into 2 parts because I really wanted, if people weren't getting frame 1, the frame to not go on, but then I didn't modify these. So this was supposed to be kind of look back at your previous slides, essentially, like how you got these numbers to figure it out. So let's actually kind of talk through some of your examples. So let's look at this one. This was the, I don't know if you guys are getting a message that, or if you're seeing a message about 10 minutes left, don't worry about that. We will finish up. But for this one, this was the x equals 2, the cut of 2.
Yeah.
So when you did a cut of size 2, then your height was 2. The height matches the cut in each of these. Even if we scroll back, that 1.5 is the cut and it's the height. And then to figure out our 4 and 6, like the length and width, what did you do?
For length and width, well, I know it said to make like your own model. So basically I just measured out 8 inches and 10 inches, like a piece of scrap paper, and just kind of made my own box. And I just measured it with a ruler.
That's great. Now you actually kind of did a physical simulation, which I really like, of this 2D part in Desmos. If we were in class, what you did is exactly what I would be having each of you do, because you're figuring out like how am I actually building it when I make a cut. And in this particular case, when that cut is 2, you can visualize like what your box looked like. I can get there, making that C to 2. So you can actually see that you have this part is your width, and then from 2 to 8, which is a distance of 6, is your length. Now, in this case, we want to think about any other constraints. In other words, when we make our cut length, we were starting with a piece of metal that was 8 inches by 10 inches. Kind of doing that the wrong way, but 10 by 8. So when we think about how we're coming up with the remaining pieces, think about it like a formula. This part, the horizontal part, is 10. You chopped out x and x. So I'm just going to type in here so that we keep track of that. That length part that we're coming up with is taking that 10 and we're chopping out an x and an x, just kind of focusing on like the bottom dimension and kind of focusing on this part. So the part in the middle that's left for the length is 10 minus 2x. You already told me that the height was x. Don't worry about those sliders. We don't really need that. No, that's not what I wanted. I just want to, you guys know what the height is. And then the width on this is going to be, we're going to use our 8. So we're going to use 8 minus, and then think about in this case, x and x is what we're chopping out from our 8 to get that remaining middle piece.
Okay. Yeah. With these slides, like slide 13, all that stuff, it asks for like the length of the box. I didn't know if it wanted me to put the ones that I found myself, like 6 and 4 or 7 and 5, whatever it might be, or if it wanted the original 10 by 8.
This one is using the original 10 by 8, but it's using that expression. So when we just found that the length was that 10 minus 2x, what they're wanting you to do is like the 10 minus 2x here. So it's saying for any size x, what would that length be? Not for any one specific x value.
Okay. So for this is like for 13, that's for length. So our length would be 10 minus 2x.
Exactly. And then they're going to kind of have you think through the width of the box. And the width of the box, we did 8 minus 2x. So once you know your x, then you can get a specific number. And then on the height, that was the x, kind of the easiest component. Then what you're going to do is build your model. Volume is length times width times height. So in this particular case, you have your x. I mean, we can do it in order if we want. Length times width times height. 10 minus 2x, 8 minus 2x, and then x. That's actually a cubic model. So think about it, it's not a parabola like we saw with the frame, but it's a cubic. But cubics can have relative max and mins depending on how they're shaped. And in this case, I'm going to drop that equation back in here. Don't bother multiplying it out in this case, because we're going to find that max and min using Desmos. And notice if we compare that back to the points that you had before, that's kind of mimicking that shape that we saw. They didn't quite look like the symmetry of a parabola, but close. Mm-hmm. So now, once we have our model, we can pinpoint like what that optimal cut is. It's close to 1.5.
Yeah, that's what I've seen, because I made, well, what I did is I submitted like my guess really, because I didn't quite make the model yet in the first slides, and people were putting like 1.5, so I tried 1.5, making my own model, and that turned out to be like 52, like the volume was 52, so that came out to be higher than all the rest.
Yes, and in terms of like when we're building models, you know, someone may build like say, okay, give me to the closest half inch or something. If we're doing a closest half inch, 1.5 would be it. But in terms of like going to a finer level of precision, we can do a little better. But when we're trying to guess what to do, no one's going to guess 1.472, right? And keep this is like rounded. So even more decimal places. So finding the exact value requires that you build a model. But when you're testing guesses, what you did is actually the best way to do it, because if you have specific guesses, you can find the actual volume for those guesses, and you can rule out like what's better or not good out of your choices. Like you can find the guesses that way.
Well, for the first slides, Taven Major, she's the one that put 1.5. I didn't really understand how she got that, like what how she found the volume and everything. So I just kind of like copied her, and like I said, I made my own model, and that turned out to be higher than all the rest, but I didn't really understand how she got that number.
Now, she may, when she's watching this, have some comments, and I'll share those comments, Taven, when you watch this. But some of it may be like she might have done some guess and check, like trying some different values, kind of like trying x equals 1. Yeah. That's my guess, but we'll see what she says, because this one was like, what do you think? So sometimes when I give this to a class, I'll see values like 2, 3, you know, like it's, people are not guessing good guesses necessarily, but it's a guess, right? I don't necessarily.
Just kind of narrowing it down.
Yeah. Okay, so hopefully that helped a little bit. Other questions for me?
I think that's about it. Okay,
great. Well, as far as today's Zoom session, this should cover everything you need in 6.4 with implicit equations, and then we'll get into a little bit of the related rates and the differentials on Thursday. So it's kind of
okay. And you said for 6.5 and 6.6, you're going to kind of like limit those to what we do.
Yeah, I'll try to I'm going to try to limit it to some geometric type ones with some volume and areas that we can kind of picture. I'm going to try to pick the ones that I think are maybe the most straightforward to understand, and then give you guys more similar problems in your homework, because your text just has a huge range in terms of what they throw at you. And they're interesting. They're just, the problems we're going to see are kind of time consuming when we look at those related. So yes, we'll edit those down. Probably going to be a smaller homework set where each one takes you a little bit longer. And then that actually wraps up our chapter. So on Thursday, I'll be talking more about how we're going to do the chapter 6 test. So it'll be online for this one, and then kind of the rules and when that'll open, and kind of get that ready so that when you guys are ready to do that, we can do it and kind of move forward. So I will see you guys virtually on Thursday. And keep in mind, I do have office hours tomorrow. If you get stuck, just take a look at the announcements for those. And then I also have office hours before class on Thursday. If you have some implicit differentiation questions, because what we're going to do is use implicit differentiation and the 6.5 and 6.6 essentially. So we need to get good at finding a dy dx and using an extra variable in our derivatives. All right, so I will go ahead and stop the video.
Okay.
And let me know what other questions you have via email in between. Thanks, Grant.
Yep, thank you.